Okay, so let's get started. So today we're going to study about on the primes for EPFP, the size of EPFP is divisible by a fixed integer. And of course, you are welcome to chat or and turn your mic on and interrupt, and I'd be happy to answer any questions or comments. So last time, Garen gave us talk about the Geller representation, like an intro to the Geller representations and how to define the additions on the points of the elliptic curves. And yes, so this slide just serves as a reminder of it, recap on that. One thing that I wanted to emphasize is when we are defining this group structures, the point at infinity, which we denoted by O, serves as an identity element. So, for example, I can actually talk about this identity element more carefully in the next slide. But yes, it's not only these real points, but you need to think about there's an imaginary, like a very high top up there. There's a point at infinity, which is basically the identity element. In this case, well, this structure, this operation gives abelian group operations on not only the real points of the elliptic curves, but also on the rational points. So if you pick P and Q to be rational coordinates, and the third point that you generate out of P and Q are also rational, is also rational. Okay, so now let E be an elliptic curve with this model that we can consider a prime P, let P be any rational prime. Then we consider exactly the same equation but modulo P. But you need to be slightly careful because sometimes this may not define an elliptic curve. In order to be an elliptic curve, it should be smooth. For example, we have some list of conditions, and that is the discriminant should be non-zero. This 4aq plus 27b squared, that's non-zero. That's equivalent to be the equation is smooth. However, now we are working on mod p, so 4aq plus 27b squared should be not congruent to 0 mod p. And some cases it might happen. So we are going to exclude these primes. And sometimes I'm going to tell prime of good reductions are those primes that are not dividing the 4aq plus 27b squared. These are the good primes. Bad primes are the primes that doesn't make this reduction an elliptic curve. Okay, so here's one example. Elliptic curve, and here's LMFDB label. So you can go to the LMFDB site and type 65A1 that you get this elliptic curve or something isogynous to this, something in a different expression of this elliptic curve. But for this elliptic curve, it is known that the rational torsion, rational points form an abelian group of C times C mod 2Z. So there's one generator, so rank is 1. We have torsion part, C mod 2Z. And now we choose P to be 7. 7 is a good prime for this one. And by the way, in this label, we have 65. And basically, you can think 65 as all the product of the bad primes. So you cannot define this elliptic curve as mod 3, mod 5, because 5 divides 65, or mod 13, because 13 divides 65. So all these prime vectors of 65 are where the bad thing happens. Otherwise, you can define the prime mod P. So that's why I chose 7, because 7 doesn't divide 65. If you think about this one, mod 7, it becomes relatively easy elliptic curves. I just forgot to write it down. And then you can just do like some hand-on calculation. You can just plug x for 0, 1, 2, 3, 4, 5, and 6, and find out if there's a y value for it. And there are only 12 of them, including point at infinity. So we have the size group is 12. I'm particularly interested, for this talk, I'm particularly interested in the size of EPFP or whether this one is divisible by a fixed integer. Okay. So now let P be a point on E. Then what is its inverse element? Because we've been only focusing on, okay, P is a point, you can add 2 points up. And I just mentioned that the point at infinity is the identity element. So what is the inverse element? That is actually the mirror image along the x-axis. Just take a point and take the negative opposite y coordinate, you'll get the inverse of that P. So that if you draw a line connecting these 2 points, that this line does not have a third point of intersection, or you can just interpret it as the third point of intersection is the point at infinity. Therefore, if you are adding this p and negative p, we get point at infinity. Technically speaking, it should be the mirror image of the point at infinity, which is we are taking as the point at infinity again. So what does it mean by p is equals to negative p? That means this point and its mirror image along the x-axis are this equal. That means that point should be on the x-axis. So the y coordinate better be 0. So 2p is O, and assuming p is not the identity, of course, if p is identity, this is also satisfied. But let's exclude the case that p is the identity. So p is a non-trivial two torsion points, that means p should be on the x-axis. So I can ask a question, how many non-trivial two torsion points, two real torsion points are there in this case? There's only one, because this curve is intersecting the x-axis only one time. But there's another case of elliptic curve that intersect 3 times, where we have one circle and a curve there, that we have 3 distinct points where the elliptic curves and the x-axis intersect. Oops. Okay, so now let's focus on this two torsion point as some like a baby example / some motivation to understand problem, the divisibility problem. So again, let E be defined by this way. That means A and B should be rational numbers. And also this delta, which I told you that should not be 0, which just defined this is called the discriminant. By the way, you can actually choose A and B to be integers as well by some linear change of this coefficient, linear change of the variables. But anyway, regardless, we want these numbers to be non-zero. Okay, and we defined this this notation last time, but I'll just go it once more. So En is all the points where if you're adding itself n times, it should be the identities. It doesn't mean that it has order n, but its order better divide n. And there are n squared points on E that has order dividing n. So there are an n squared point in this group. And let us take each pi has x coordinate and y coordinate as xi and yi. Then we can consider a field extension over Q that is putting all these x1, y1, x2, y2 all the way up to xn squared, yn squared. This is going to be a very huge field, I know. But we call this one as an n division field and denoted by QEN. And this one has a lot of good information about the Geller representation, which I'll soon explain later. Okay, so let's talk about this two torsion point and how to tackle the two divisibility problem. So first of all, let fx be the right-hand side of this one. Okay, and let us assume that we can split it completely as xe1, x minus e1, x minus e2, x minus e3. This e1, e2, e3 may be rational, maybe non-rational, maybe complex, maybe real. It can be any numbers, of course. So what is e2? Well, there are only 4 points. Of course, we have point at infinity, the identity element that has order 1 dividing 2. And we should have 3 non-trivial two torsion points. And as we saw in the previous slide, that if it is a non-trivial two torsion point, the y coordinate should be 0. It should be on the x-axis. So in this case, y1, y2, y3 are just all zeros. So two division field as Q, which was E1, E2, and E3, we just need to introduce these 3 numbers. And this discriminant that I mentioned above can be actually written in terms of E1, E2, and E3. You just take 2 distinct EI and EJ, take a subtraction, do everything, multiply them all together and take a square. And you can imagine what happens wrong if E1 and E2 are equal. Then discriminant becomes 0. That's equivalent to that this equation has a repeated root, and that's where the smoothness fails. So we better make E1, E2, E3 are all distinct numbers. And because this delta is rational number, but we can consider the square root of delta, which is now E1 minus E2 times E1 minus E3 times E2 minus E3, which may be rational or maybe not. But regardless, that should be an element in QE2. Why? Because QE2 is generated by E1, E2, E3, and this number is generated by that E1, E2, and E3. So this one should be a subfield of QE2. And let G be the Galois group. Then how does this Galois group work? It basically acts on E1, E2, and E3. It should be shuffling them because I told you QE2 should have these three numbers, and the Galois automorphism in this group can only shuffle E1 and E2 and E3. It cannot do anything else. That means because we can consider what is the group structure shuffling E1 and E2, E3. That one is symmetric group with three elements. So G can be understood as a subgroup of S3. Maybe it can shuffle however it wants, so that G is the full group. Or maybe it cannot shuffle anything at all if E1, E2, E3 are all rational numbers, because G should respect the rational numbers. So this kind of identification, like Galois group as a subgroup of S3, is really helpful to understand the two torsion point. And one last thing is, let sigma be a Galois automorphism, then we can consider sigma on square root of delta. That's equals to the sign of sigma, viewing sigma as an permutation, because we can view G as a subgroup of S3. Every Galois automorphism can be now understood as a permutation on E1, E2, and E3. If, for example, sigma only switches E1 and E2 but not E3, then sign is -1. And if E1 and E2 are switched, then this one has an opposite sign, but the other two has the same sign anyway. In this case, we have the sigma square root of delta should be negative sigma square root of delta, negative square root of delta, which matches up with the sign of sigma square root of delta. But if sigma, like ascend E1 to E2, E2 to E3, and E3 back to E1, then if you apply to this number, square root of that one, then we are making negation twice, so we get the same number. So the sign is again positive, and also it fixes square root of delta. Okay, so that's some list of observation that might come in handy to understand the two torsion points. So there are four cases. Just to remind you, this f of x is the right-hand side of this one. And we are only considering the right-hand side because two torsion points should have y coordinate 0. We only need to check when this one has the roots of this one, because those are all the two torsion points. So this f of x, because it's a cubic equations, we have four possibilities. Case number one, the easiest one, it can be split completely over Q. So E1, E2, E3, they are all rational numbers. In this case, QE2 is, of course, just a rational field because E1, E2, E3 are all the rational numbers already. And because G is a Galois group, so it should fix rational numbers. That means it is fixing every element at the two torsion point. It cannot switch E1 and E2, or it cannot do anything with it. That means G is a trivial group. Case number two, this fx split into two parts, one with linear and the other one is quadratic. So in this linear E1 case, this E1 should be fixed because E1 is now a rational number, but this G can swaps E2 and E3. So in this case, QE2 is just a splitting field of the later part, XE1, XE2, and XE3, so it's a quadratic extension. And G fixes E1 but switches E2 and E3. That means G can be understood as a permutation, switching 2 and 3. That's isomorphic to Z-mod 2Z, of course. Case number three, fx is irreducible, so it's a cubic, but we cannot break it into smaller degree functions. But square root of delta is rational. Since square root of delta is rational, we should have sigma square root of delta is square root of delta for any sigma in this group. And recall that the sigma square root of delta is sine of sigma square root of delta. It's meaning that all elements in this group should have sign +1. And in the group of S3, we have two subgroups that every element has sign +1, which is the trivial group or alternating group. It cannot be the trivial group because f of x is irreducible. And this one should be the splitting field. That means it cannot be a trivial group. So it better be the alternating group, A3. So it can shuffle E1 to E2, E2 to E3, E3 back to E1, like rotating. In this case, QE2 is a cubic extension of it. And finally, if f of x is irreducible and square root of delta is not rational, then G can shuffle E1, E2, E3 however it wants without any restrictions. So in this case, G is the full S3 group because you can shuffle these three elements. And S3 can be identified as GO2 sigma 2Z, which has 6 elements. So QE2 over Q is a degree 6 extension. So for two torsion points, we only have these 4 cases. It can be understood pretty concretely and nicely, mainly because two torsion points has y coordinate 0. So we can ignore this y part and we can only focus on how this right-hand side of the elliptic and this x part split, or how this part like decomposes. Okay, so that's some like an how should I put it, some basic start for this divisibility condition kind of idea. But any question, please let me know. That I'd be happy to answer. Okay, otherwise, let's move on. So now let's talk about some Geller representation. So let P be any point on the elliptic curve that can be written as x coordinate xp and y coordinate yp. We already checked. I mean, Garen showed in his slides last time. Also, at the very first slide, we talked about we can add point to itself how many ever times it want. And we denoted by this square bracket P. That is, you're adding P itself n times. In fact, this map is rational. That means you can find some rational functions, fm, gm, so all the coefficients is rational, so that this multiplication by n map can be just understood as evaluating this fm and gm with xp and yp coordinate. So for example, this rational multiplication by 2 map, that can be written pretty simple, where lambda is 3xp squared plus a over 2yp, where a is the coefficient here. However, if you're trying to write down multiplication by m map in general as a rational function, it becomes pretty complicated. So here are 2 cases, relatively easy. But if you're just like very much ambitious and try to come up with a higher number, it can be very hard. But the important thing here is, regardless, is it is rational. Oh, the coefficients are rational. Why does it matter? Because multiplication m map is rational, sigma and Geller automorphism, and this multiplication by m map can interchange. So this MP means you bring xp and yp, you add, subtract, multiply, divide by some rational numbers. And if you're applying sigma to that one, that's going to respect all these multiplication, all these add, subtract, multiplication, division by the rational numbers. It will only work on the xp and the yp. Therefore, we can switch this idea. I mean, we can switch this operations. The sigma is only working on the xp and yp, so we can first consider sigma p, and then multiplying by n, we get the same thing. So these two are equal as the key idea to define the Geller representation, which is based on that this map is rational. But in particular, in an earlier slide, I just chose any point on elliptic curve. But what if P is a point in EX? So P has order m, or maybe dividing n. Oh, I just got a question. What John is saying is completely correct, but we have to make sure that elliptic curve is in the form of yes. So mainly elliptic curve can be written as this way. However, sometimes we express elliptic curve in a slightly different way. So long bias truss equation form has y squared as like plus xy, or some xy terms and some x squared term. We have some extra terms. You can always make it into the short bias truss equation, which I've been showing. In that case, I mean the short bias truss case, then we can just let y be 0 to make it as a 2 torsion point. However, in general, long bias truss equation, this may not hold because this is not symmetric along the x-axis. And thanks for pointing out, Gary. Okay, so now let P be an n torsion point. So first of all, this point at infinity is fixed by sigma, because technically speaking, this point at infinity, when you think it as a projective level, then it's just 0, 1, 0, or 0, 0, 1, which is a rational numbers anyway. So sigma should respect the identity element O. because I'm assuming P is an M torsion, so MP is identity. But we already saw that M and sigma can interchange, so M sigma P is also the identity. That means sigma P should be an M torsion point. So this idea tells us that GQ, because sigma is some random Galois automorphism, GQ must be acting on EM. If we choose a sigma Galois automorphism and choose any M torsion point, that's going to generate another, maybe the same, or maybe another M torsion point. So this gives a map, rho EM, which I'm going to call it rho EM, from GQ to the automorphism of EM. So each Galois automorphism is shuffling M torsion point, so it can be identified as an automorphism on the M torsion point. However, upon the choice of Z mod MZ basis, EM can be identified as Z mod MZ times Z mod MZ. So upon the choice of basis, this automorphism EM can be identified as GO2 Z mod MZ. And we're going to denote this image of rho EM GQ inside the GO2 Z mod MZ as GEM, which is not uniquely defined because it's defined upon a choice of basis, so it is defined up to conjugation. But I don't really care about defined up to conjugation because I'm usually interested in the size of GEM, not how it exactly looks like. So from now on, I'm just going to assume GEM is some specific group. And this rho EM is called the mod M Galois representation. And this will be extremely useful tool to understand the prime divisibility condition. By the way, this rho EM factors through Galois group of QM torsion and division field. So that means this GQ can be replaced by this one, and everything works still the same. In particular, if GQ is fixing QEM, then every element in GQ will be the identity element here. So you can quotient it by GQ by, this GQ is, by the way, absolute Galois group, this GQ by GQEM, so the absolute Galois group over QEM, and still this Galois representation works nicely because that one is inside the kernel, and that quotient is nothing more than this group. So you can consider rho EM, the mod M Galois representation from the full absolute Galois group from GQ to GL to Z mod MZ. However, for a computational purpose, because it's kind of hard to imagine GQ, we can just consider it as a Galois QEM because we know there should be a finitely many numbers to generate QEM. And in most of the cases, much more like concrete and easier numbers to deal with. Okay, so that part is about the Galois representation. I'm going to move on to some quick crash and algebraic number theory. But if you have any questions so far, please let me know. I'm happy to answer. Okay, then let's do some quick crash course in algebraic number theory. Yes, it's actually a helpful time for me as well because I took algebraic number theory quite a long time ago and mostly forgot. And then I'm currently working with a few other postdocs, and then we are supposed to write some proof about the algebraic number theory. And then with this experience and with this opportunity, I could do some like a revision, and it really helped me understand and lay down the foundation again. So yeah, I'll just go over very basic facts about the algebraic number theory. So let K be number field and OK be the ring of integers. P be a rational prime, then this PZ is a prime ideal in Z. Then naively, we can expect this POK. So now in this OK multiplying with P, hopefully there should be a prime ideal, but not necessarily in most of the cases. But OK is a Dedekind domain. It means you can factorize any ideal into the prime ideals uniquely. It's like a UFD. It's like every integer can be uniquely factored as a prime number. And now this is replaced by the ideal. So any ideal, POK might be a prime ideal or maybe not. And that can be uniquely factored into the product prime ideals as follows. Then we have three possibilities. Case number one, POK is inert. Here I said G is 1 and E1 is 1. That basically means POK is still a prime ideal. In that case, we call P an inert prime. Case number two, P ramifies if one of the exponents is greater than 1. As long as you see one prime factor has some non-trivial exponent dividing this POK, then we say this P ramifies in this field. And case number 3, split. If you have multiple prime on the right-hand side, multiple prime ideals on the right-hand side, all the exponents should be 1. None of them should be greater than 1. In this case, we say P split. And from now on, we're going to write this EI, this exponent, as E of PI over P, and that's called the ramification index. And the name explains everything. If ramification index is 1, that's either inert or split. If ramification is greater than 1, P ramifies. Okay, so for the prime ideal, PI dividing POK, that means if I go back to the previous slide, that PI occurs on the right-hand side. And in that case, we usually say this PI is lying above or lying over P. I think it's quite a useful terminology, so I wanted to introduce. So for PI lying above P, one can confirm that this residue field, OK by PI, this one should be a field because this is not only a prime ideal, but should be a maximal ideal, in fact. So this is a field, but actually it's a finite extension of ZP. So on the base level, we have ring of integers, which is Z, and we have a prime ideal, which happens to be maximal as well, because we are choosing P non-zero. Then Z mod P is a field FP. When the upper level, we are extending Q to K, then we have a ring of integers OK, and we have a prime lying above P. Then that's also generate the field, a residue field, OK over PI, and that is a finite field extension over FP, the base level. And that degree of extension is denoted by Fi, and we call it the inertia degree. And here's a very beautiful and nice theorem. If K over Q is a finite extension, then this degree can be written as is equals to the sum of the prime ideals of the ramification index and the inertia degree. So in the earlier slide, if POK can be decomposed into this way, each prime up to G, we can bring EI, and we can also find the Fi, multiply them, and add them up all together, and that encodes the information about how large K is compared to Q. So the degree of K over Q. Even the better thing is, if K is a Galois extension over Q, then this EIs, no matter which prime ideal you choose above P, these EIs are all equal to each other. Also, the inertia degree, no matter again which prime ideal you choose from P, lying above P, they're all equal to each other. So this equation can be written as a very nice way that the size of KQ is EFG. I actually like how they chose E and F and G for this quantity, so that it now becomes like some alphabetical order of some alphabet, some random alphabet. But yes, it turns out to be EFG. And we're going to see some easy examples to see what happens if K is a quadratic extension. So let K be Qi, which is, of course, the easiest example that we can imagine. In this case, the ring of integers is known to be just a Gaussian integer, C joins I. Then we have 3 possibilities. Yes, P ramifies, and P splits, and P inert. And how is it determined? It's simply determined by whether P is congruent to 1 or 3 mod, or maybe even. P is 2 is the only even case. So if P is 2, then we have ramification index 2. Inertia degree, I didn't show how to calculate the inertia degree, but that is 1. That should be 1, because we know that the product of all these 3 numbers should be 2, because that's the degree of K over Q. And G is the number of prime ideals appearing here. There's only 1. And of course, it can only be 1 because we already took 2 here, and the product of all these things should be 2. If we are choosing 3, P is 3 is congruent to 4, that's inert. In that case, E, well, I don't see any exponent, so the ramification index is 1. I see only 1 prime, the inertia degrees, the number of prime is 1. So we can expect that the inertia degree should be 2. I didn't show you how to calculate the inertia degree, But based on the formula that I introduced in the earlier slide, we all agree that it should be 2. And finally, if I choose P is 5, then no ramification index, no exponent, so 1. There are 2 primes appearing, actually A minus BI, my bad. So G should be 2, F should be 1. So in particular, if K is a finite Galois extension of prime degree, we only have 3 possibilities. E is that prime, F and G are 1. F is that prime, E and G are 1. G is that prime, E and F are 1. And there are very few possibilities. And by the way, if P, well, this case is P split, but P split and also, of course, P split means the ramification index should be 1. But if the inertia degree is also 1, so we say P splits completely. It just breaks into the number of the prime factors as large as it can be. Okay, so I think this is a good example to see how this EFG interplay to encode the information about the degree of extension. Of course, it becomes harder if K over Q is not Galois, or maybe the K over Q degree is not a prime number, then this calculation becomes a little bit more trickier. So, and here's some like a one-page summary note of maybe some algebraic number theory. Maybe the first midterm amount of algebraic number theory, first 5 weeks about algebraic number theory, I guess. So K is a quadratic field. Everything is studied very much concretely. So ring of integers, it should be like this, depending on whether D is congruent to 1 or 2, 3 mod 4. Of course, D is square free. That means D cannot be congruent to 0 mod 4. And we define delta K, which is the discriminant of this field. That's D or 4D. Then for a P on odd prime, odd rational prime, whether P is ramified, split, or inert, depending on whether P divides delta K or the Legendre symbol delta K over P is 1 or negative. So that's why Legendre symbol is important, because it actually tells us the splitting behavior of a prime in each field. And basically, Legendre's field is talking about, Legendre symbol is talking about whether a certain number is a quadratic residue. And we can naturally think about the extension of the Legendre symbol. What about like cubic extension? What about the quartic extension, some higher degree extension? Then, of course, we can somehow define it so that it encodes the information of the prime splitting behavior. That can be one thing one can consider. But yeah, Legendre symbol is particularly useful and important. And if you want to revisit the Legendre symbol, then you can go to Google and type the Legendre symbol. It has a very nice, simple definition, but it has a lot of very meaningful stuff about the number theory. By the way, I usually make an analogy like a Legendre symbol is when elementary number theory transitions into algebraic number theory. I don't know whether the other people may agree or may not agree, but I think that's a very huge, like a discovery to make it not just working on each number, but now start working on the field of extensions. And yeah, thanks for nodding, Garen. And yeah, it actually reaffirms my conviction. Okay, so now let's talk about the Frobenius class. And this is quite a dense information, but I'm just trying to summarize as much as possible. So maybe some part, if you get confused, you can always ask me, or you can revisit the textbook. But I'm just trying to introduce the minimal amount of knowledge to talk about the Chebyshev symmetry theorem. So let K be a finite Galois extension and G be the Galois group. We are choosing P unramified because if P ramified, then it's getting more complicated. So P can be inert, P can be splitting, but P should be unramified. P should not be ramified. Now let X be the set of all primes lying above P. Of course, if it is inert, then X has only one element. If P splits, then X will have that number of prime ideals. First proposition, GX on X transitively. That means if you just choose any prime lying above P, you can find the Galois automorphism at this Galois K over Q, sending P to Q. Second proposition, for each prime P, there is some Galois automorphism with the property that sigma P is congruent to X to the power P mod P for any X in the ring of integers. As such, sigma of P is called the Frobenius element at P. Finally, if P and Q are prime ideals lying above P, sigma P and sigma Q, the Frobenius element, are conjugate to each other. So you can find some tau in this Galois group where tau sigma P tau inverse is sigma Q. So all these three propositions says if you just choose a rational prime like 2, 3, 5 at the a rational fluid level, as long as it is unramified, then we can have many different prime. If it is splitting, then we can have multiple primes lying above. If it is inert, there's only one though. Then we can consider the Frobenius element in each of these prime ideal, but they're all conjugate to each other. So we can define the conjugacy classes of all these Frobenius elements, and that's called the Frobenius class at P. And we write it down as Fro P. Okay, so let's check some baby example to get a better idea of what's really happening. So let K be Q adjoint square root of -3. It's a simple example. Then Galois group has only two elements, namely the identity, just fixing everything, tau, complex conjugation. And then we now need to talk about how this prime split or inert. That is, if I go back to the earlier slide here, because now I'm choosing D congruent to -3. That is this case. In this case, delta K is -3. So the splitting behavior of a prime relies upon the Legendre symbol -3 over P. However, we have a very nice property or theorem called the quadratic reciprocity. So for this case, I'll skip some details about the quadratic reciprocity, but this is actually equal to Legendre symbol P over 3, inverting and also ignoring negative sign. That is 1 if P is congruent to 1 mod 3, or -1 if P is congruent to 2 mod 3. Another way to put it is, if P is congruent to 1 mod 3, like 7, then P is splitting in this field. However, if P is congruent to 2 mod 3, like 5, then P is inert. What about 3? We don't care because that one is ramified. I told you if P divides this number, then that's the case when P ramifies. And in order to talk about the Frobenius class, I want an unramified. Right? So ignore the P equals 3 case. For notational convenience, let alpha be square root of -3. And let's work on each case to see how Frobenius class works. By the way, here we have only two elements, and we can see this Galois group as C mod 2Z, which is a abelian extension. Because it's an abelian group, every element forms its own conjugacy class. So we have two conjugacy classes here, set of 1, set of tau. Now let us see how Frobenius at P turn out to be. So let P be 5, then P is inert. And let sigma be the Frobenius element, P. Actually, Frobenius element Fp. In this case, because P is inert, there's only one prime lying above 5, which is just 5 itself. So we can talk about Frobenius element at that 5, which is sigma. I want this, so if I go back to the earlier slide quickly, the sigma P, the Frobenius element, should satisfy sigma P of X is congruent to X to the power of P. So now this P should be 5. So I'm going to choose X to be alpha because alpha is some easy numbers to deal with it. Then alpha to the power of 5. Oh, that's alpha to the 4 times alpha. And you can see alpha squared is -3. So it becomes -3 times -3 times alpha, which is 9 alpha. And the sigma should satisfy the property that sigma alpha is congruent to 9 alpha mod 5 OK. So we have two possibilities. Either sigma is 1 or tau, because there are only two elements. But doing some calculation, we can convince ourselves that sigma alpha should be negative alpha. Sigma should be a complex conjugation. Why? Because if sigma alpha is negative alpha, then I have negative alpha is congruent to 9 alpha mod 5. Of course, 10 is divisible by 5, so negative alpha should be congruent to 9 alpha mod 5 OK. So that means sigma should send alpha to negative alpha, that the sigma is a complex conjugation because I chose alpha to be this number. So probe at 5, probe class at 5 should be tau. What about P7? Well, because P7 is congruent to 1 mod 3, it should be splitting. So let P and P prime be the primes lying above little p, rational P. And now I need to make a choice, but it doesn't really matter because these Frobenius elements and each P and P prime will be conjugate to each other. And because this one is an abelian group, only element itself is conjugate to itself. So in this case, I can just choose P, but if you choose P prime, we'll end up having the same result anyway. Okay, so we have alpha to the power of 7. Again, if you do the same calculation, you'll have negative 27 alpha. And I want to have my Frobenius element at P to be sigma alpha is congruent to negative 27 alpha. Well, actually, I made a typo here. It should be P. It should be not 7 OK, but it should be this one. But if it is congruent to this one mod P, because P is lying above 7 OK, still this condition will be satisfied. Yeah, I just made a mistake when I was writing down this one. But still, if it is congruent to this one mod P, it'll be congruent to mod 7. So again, we have two possibilities. Sigma alpha should be either alpha or negative alpha. In this case, sigma alpha better be just alpha. So the alpha is congruent to negative 27 alpha. And yes, of course, because 28 is divisible by 7. So alpha should be congruent to negative 27 alpha mod 7 OK. So in this case, my sigma should be the identity element. Therefore, from 7, Frobenius class of 7 should be the identity element. In fact, if P splits completely, so in this case, of course, if P splits, then it should be splitting completely because it's a quadratic extension. Splitting means there should be at least one prime. If we have degree 2, then of course, that's the only case where primes splitting completely. But in general, it may not be the case. However, if P splits completely, so that the number of the primes lying above P is equal to this degree of the Galois extension, then the Frobenius class should be always the identity element. I'm not going to use this fact for today's exercise, but that will be maybe used to work on some related problems. Maybe about the cyclicity problem, we need to use that fact. Okay, so I think we have some good exercise experience with the Frobenius class. Now I want to introduce the Chebotare's density theorem. So let K over Q be a finite Galois extension and G be the Galois group. C be stable in their conjugation. It doesn't need to be a conjugacy class, but it can be a union of conjugacy classes. Then the number of primes up to X where P is unramified in K and rho P is contained in C, because rho P is a conjugacy class, it's not an element, so we need to use the containment symbol. That's roughly C over G times X over log X. Because the number of primes up to X is roughly X over log X, this one tells the density of primes with this property is size of C over size of G. By the way, P is unramified. Yes, you can actually replace this one by just P in K because there are only finitely many primes ramified in K anyway. So even if I include these primes that are ramified, this asymptotics will not be affected. But usually, conventionally, we always say just P is unramified. But even if you consider P ramified case, there are just very few of them, so it will not affect the asymptotics in general. So with the previous example, K is Q with square root of -3. There are two conjugacy classes, 1 and tau. And let C be one of them, either one of them. Then by the Chebotare's density theorem, that's roughly 1 over 2 times X over log X, because there are two elements in G, and each conjugacy class only have one of them, as X goes to infinity. And of course, that matches up with the prime number theory in arithmetic progression. Because whether P splits or not, or if rho P is complex conjugation or is the identity, only depends on whether P is congruent to 1 mod 3 or 2 mod 3. How many primes are congruent to 1 mod 3? We can expect half of them. How many primes are congruent to 2 mod 3? Again, we can expect half of them. It's actually the Dirichlet theorems of arithmetic progression types of idea, but actually Dirichlet's theorems on arithmetic progression doesn't tell you about the density. The prime number theorem and arithmetic progression tells about the density, and yes, we can expect half of them as congruent to 1 mod 3 and the other half is congruent to 2 mod 3. And the Chabotar density theorem confirms that effect. Yes, it should be half of and half. Okay, so now we finally arrived to our original question at the title of the talk. So let E be an elliptic curve and be a positive integer. What is the density of primes for which the size of EPFP, which I showed very early, like the second page of this slide. So, and yes, size of EPFP is divisible by n. In the earlier case, in the earlier slide, we saw a particular elliptic curve where the size of E7F7 is 12. So in this case, that one is divisible by 2 and 3. But in general, if I just pick a random integer m and study how often this number is divisible by m, what is the density? So we use a Galois representation mod m. So first we consider mod m Galois representation and define the image by Gn. I choose P not dividing M and E. I didn't mention what NE is, but NE is basically the product of bad primes. So in order to talk about the EPFP, I need to choose a good prime. So NE is basically a product of bad primes. So P doesn't divide NE means P is a good prime. So we can consider the reduction. And I also want P not dividing M because in order to talk about the Frobenius class in this field, I want P to be unramified. And this field, primes that are ramified are those that are dividing M. Yes, so I need to choose P that are not dividing M and E. Of course, there are only finitely many of them, so it will not affect our asymptotics anyway. Okay, Fro P forms a conjugacy class here. And because this is like an injective group, so we can consider GM as a subgroup of here, which is isomorphic to this one. So Rho and Fro P will form a conjugacy class in GM, but GM is a subgroup of GL2, so we can define determinant and trace. Like any matrices, we can define the determinant and trace. And a very nice property is that determinant of this Rho and Fro P is congruent to P mod M. And trace is congruent to P plus 1 minus EPFP. And this one has so much nice meaning. This trace has so much important meaning in the number theory, so we have a special name for it called the Frobenius trace. Yes, as the name suggests, trace of a Frobenius element. Frobenius class, so Frobenius trace. So Frobenius trace is a deep relationship between size of EPFP, so AP is congruent to P plus 1 minus size of EPFP. But what is our goal? Our goal is to study when this number is divisible by n. That is equivalent to this APE is congruent to P plus 1 mod n, assuming this is 0 mod n. So I want to find all Frobenius traces where APE is congruent to P plus 1, but P happens to be the determinant. And we don't need to worry about whether it is closed under conjugation or not, because in order to apply the Chebotare's density theorem, I need a set C that is closed under conjugation. And yes, it is closed under conjugation, because if you have a matrix and then conjugate it, then the determinant and the traces are preserved. So if I impose a condition that the Frobenius trace is P plus 1 and determinant is P, that will be closed under conjugation. So if I define this C, a subset of this GM, where determinant of M, that should be P, plus 1 minus trace, which is this part, is congruent to 0 mod M, that's going to measure the density of primes such that determinant is the Rho and for PSP, and trace is P plus 1 minus EPFP, which is divisible by n. The size of EPFP will be divisible by n. So the density of such primes to this question is the size of C over size of GM. Yes, so it just sounds like it's some abstract math. So again, let's work on the easiest case. Density of primes where EPFP is even. So in this case, I need to choose P not dividing 2 because I want to talk about the mod 2 Galois representation. So M is 2. And of course, the conductor, NE, the bad primes. So that means P is an odd prime, and determinant the row E2 row P. That should be P, which is odd, so that should be congruent to 1 mod 2. And yes, I want this one to be even, size of EPFP to be even, but P is odd, so P plus 1 will be even. That means I want the APE to be even. So we want to count prime for AP as even. So we define this C set, which is all the elements in G2 such that trace is congruent to 0 mod 2. Of course, this is closed under conjugation because conjugation preserves the traces. And one of the early slides, we talked about the possibility of G2. I told you there are only 4 possibilities based on whether Fx, the right-hand side of the elliptic curve, splits or not. And G2 has 1 element, 2 elements, 3 elements, or 6 elements. Or if I interpret everything into the GL2Z mod 2Z subgroup, then we have these cases, or conjugation of these cases. But as I told you, I'm only interested in the size of G2. I don't care about the conjugation. Just bring some concrete matrices. So if G2 has only 1 element, fixing all the rational 2 torsion points, and fixing all 2 torsion points, then there's only 1 element, and that element has trace 2, which is even. So the density becomes 1. That is, every prime makes EPFP is even. If G2 has 2 elements, but you see their traces are again both 1. In that case too, every prime EPFP will be even. If G2 had 3 elements, then only one of them has even trace, not the other 2. In this case, we only have 1/3 of the primes that makes EPFP even. And finally, if G2 is the full group, you can count there are 4 elements having the even traces, and these 2 elements are the odd traces, so the density becomes 2/3. So one observation here is EPFP, no matter which elliptic curve you choose, the size of EPFP is even infinitely many times because all those densities are positive. But of course, the question is, what kind of sorcery had happened in the earlier 2 cases guaranteeing all the primes make EPFP even? Is there a way to understand the underlying reason why we always have even EPFP in this case? So here's a proposition. If the size of G2 is less or equals to 2, then every good prime, the size of EPFP is even. In fact, it actually relies upon a relatively simple fact, that is, EQ torsion, so rational torsion subgroup, sit inside EPFP. So there is some injective group you can define where this is inside this. If G2 is 1, it has only 1 element, we show that all the 2 torsion points should be rational. And 2 torsion points form Z mod 2Z times Z mod 2Z group, and all of those are rational. So this Z mod 2Z times Z mod 2Z should be sitting inside this EQ torsion, which just means this is sitting inside this one as a subgroup. That is, 4 should be dividing the size of this EPFP. So of course it should be even. If G2 has 2 elements, that is fixing, say, E1, but switching E2 and E3, it has at least 1 rational 2 torsion point. Because it has a rational 2 torsion point, Z mod 2Z should be a subgroup of EQ torsion. That means Z mod 2Z should be a subgroup of EPFP. So 2 must be dividing the size of EPFP. So in this case, the Chebyshev density theorem doesn't really explain why the size of EPFP should be always even. But size is always even. But if we now interpret this one with our earlier idea of how this one looks like based on the splitting behavior f of x, it just becomes quite a simple and nice fact. Sorry, I missed some comments from here. I write the note, which is about geometric understanding. Oh, okay, that's exciting. I'm really excited for that one. And maybe I've already spent 1 hour, so here's a very last slide. So we just talked about the distribution of primes where EPFP is even. But what about in general? EPFP is divisible by some prime number Q. Of course, you can make it into any composite number, but let's start with the easy case prime number. Suppose that the size of GEQ is the full Galois group. So GEQ is the GL2Z mod QZ. And by the way, it is known that if you choose Q large enough, this GQ should be always the full GL2 group. So in this case, we want to set up C to be element M in GQ, where determinant of M plus 1 minus trace M. This is the size of EPFP for choosing M to be the Frobenius class. And we want that to be congruent to 0 mod Q. And it's pretty much easy to show that it is closed under conjugation because determinant and traces are preserved under conjugation. So you can just choose specific determinant, specific trace, and each of them is closed under conjugation. And this is just a union of those things. Prove that the size of C is 2 times this one. This can be done by this fact. Actually, there is a very nice formula about counting the matrices in GL2Z mod QZ with the fixed determinant and fixed trace. So you can just run over all the D and T satisfying the property. You can find this size. Therefore, by the Chebotar's density theorem, the density should be this one over the size of GL2Z mod QZ, which is Q squared minus 1 times Q squared minus Q. And you can simplify to get this one. So if I'm choosing Q large enough, then numerator is just like Q squared. And denominator, we see Q to the power 3, that's the largest degree. So the density is roughly 1 over Q. And that, of course, matches our intuition. If I ask you, what is the probability that a randomly chosen integer is divisible by 11, then probably you'll say it's 1 over 11. You just have 1 through n, choose all the numbers divisible by 11, then the ratio converges to 1 over 11. And likewise, the size of EPFP is so well distributed, so well randomly distributed. So if GQ is the full Galois group, then the density of primes where EPFP is divisible by Q is roughly 1 over Q, as if you're choosing one random number from whole integers that should be divisible by Q by 1 over Q. Of course, this doesn't work if Q is chosen like small number, because we already saw in mod 2 cases, none of them happens to be 1 over 2. But if Q becomes a relatively large number, then it becomes very close to 1 over Q. And that's the end of my talk, and I really appreciate your attention. And if you have any questions, I'd be happy to answer them.
So I do not have a very specific question right now, but in fact, truth be told, I think we too can really discuss about this theorem. I mean, the behind the of course algebraic structure of for sure, but also the very the proper understanding regarding this the important the topic. So I really actually really enjoy to imagine what is actually really behind. So I'm very happy to to share my the intuition next time in this seminar. But it's not just over by just one time in a sense that I think the behind the structure is really the deep in my perspective. So I think it could be very the enjoyable for all of the participants, but very roughly speaking, in my perspective, for today's the very heavy algebraic the machinery is really just nothing but just a donut. Truth be told, donuts rotating 100 degree. That actually gives everything today. I'd like to really explain what I'm really realizing from today's talk. I really actually like it. Yeah, I really appreciate it.
Yeah, I'm excited to learn about some geometric intuition about this one because I've been always working on just counting the matrices with certain properties. It's really hard to imagine some geometric reason beyond this one. Also, the good thing about that all the problem just simply boils down to counting the matrices is there's some good possibility to incorporate some research for an undergraduate or a graduate student because I can't just let them okay, here's some motivation. I want you to count the matrices with certain properties, and they can do it. They can put some number theoretic understanding or prerequisite to that one to create the paper. So I think this is quite a good research topic. I mean, for divisibility cases already very much well known, but you can consider some other variant of this kind of thing. As long as you can define a property about a group, a abelian group. So for example, Alina Kokar, she is a wife of my PhD advisor. She's also a math professor at UIC. she studied the distribution of prime, not only this is divisible by a certain integer, but when this is square free, or when this is cyclic group, or when this has like um, some other relevant properties that one can imagine. And all of these kind of problems in the end boil down to just counting the matrices, and she already made a huge contribution to it because it's relatively easy. The core part is relatively easy. Writing down the whole paper is a little bit tricky part though. I believe I can invite some more like a possible research, and I'd be happy to like invite some people through your like a math YouTube communities, and it'll be my pleasure to advise them.
Yeah, so one like this side, like the note for the like the people who might watch this like the record like the video was so one of my like the bias like the experience before when before I studied my own mathematics I mean geometry for my PhD was so I felt like the people who study number theory is just a genius because I have really no idea how to understand Galois representation so what they are really talking about. Yeah, I indeed still admire the people who study this like actually very like the abstract and fancy mathematics for sure, and this is very worthwhile like the mathematics as well. But at the same time, I really couldn't get it. So what really motivates the people who really like to study this like the fancy topic? So are those like the people are definitely like the different like the people from my like the neighborhood? I was thinking something like that. So nowadays I my like the perspective completely like the change in a sense that so those are some like the very like the simple does not mean trivial. So simple
Of
like
course.
the concrete observation to really understood what was going on to make these types of the very heavy algebraic like the abstraction and I begin initiate to enjoy those really simple observation where does this was really coming from and I kind of like the get the idea that if one just look at the Torah so indeed all those like the presentation today I learn is really just rotating the torus 100 like the degree without any like the fancy like the knowledge. So yeah, I'm very happy to actually share these types of perspective and also get some critique and hopefully this could be also fun for the participants as well. Yeah, so that's what I want to say.
I think
Um,
the feeling is mutual. I mean, probably Garen might be agreeing or not, but I've always thought the geometers are so much genius too. Like, how do they imagine something like that? Like, whenever they talk about the schemes and stuff, I also complain to my wife, who doesn't know anything about mathematics, but she was thinking, "Hey, isn't geometry easy because it's all about the drawing?" And then, uh, okay, but can you draw something like higher dimensional, like something where moduli space, so every point represents some isomorphism class of elliptic curves? I cannot imagine that one. And then, yes, I like to build some geometric intuition even further because that really helps me. So I've been like working on these kind of problems like an inertia. Like, okay, I started working on this one. I just keep pushing myself in that direction, but I never questioned my origin of all these problems. Like, okay, my advisor gave me this problem. I know how to work on it. I can work on some relevant problems, but I know how all these ideas came from. And I like to read your note and also like wait. So much looking forward to your talk maybe next time. If you are going to talk about some geometric intuition for this one, that'd be really beneficial for me too as well.
Yeah, so even I'm using a lot of like the analysis, heavy analysis tools in my research for sure, but the people who is really doing analysis treat me as a kind of the algebra like the people. In a sense, I actually do more like algebra than analysis, truth be told, and I really kind of like it. So yeah, so but I hadn't know like the chance to take the any like the number theory courses before. So yeah, this is really my first time to like listen what is algebraic number theory, those kind of things. Yeah, but I really yeah appreciate for this like the algebraic inspiration as well. Yeah. So any other comments or questions for today for the record? So if not, we can stop the record here and we will meet in 2 weeks.